എന്തെങ്കിലും ടോക്ക് മറ്റൊക്കെ വേണമെങ്കിൽ ഷെയർ ചെയ്ത് കൊടുത്താൽ കയറാൻ താല്പര്യമുള്ളവർക്ക് എടുത്തോളാൻ പറ്റും കേട്ടോ. കാരണം ഈ പിള്ളേരൊക്കെ എത്ര പറഞ്ഞാലേ അപ്പൊ നമുക്ക് യൂസ്ഫുൾ ആവുന്ന ആൾക്കാർക്കെങ്കിലും ഒന്ന് പ്രയോജനപ്പെടുത്തും. ആ, ആ, അതെ അതെ. ആ, ഓക്കെ. അതൊക്കെ കയറി നല്ല നിങ്ങൾക്ക് കിട്ടുന്ന സാധനങ്ങളൊക്കെ നോട്ട് ചെയ്ത് അതെ 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 അതെ. ഓക്കെ. ഇതിനകത്ത് കയറണമെന്നില്ലല്ലേ? കയറാനില്ല. അല്ല പിന്നെ കട്ട് ചെയ്താലും മതി. അല്ല കുറച്ചു നേരം നമ്മൾ ഇത്ര പോലെ കിടന്നോട്ടെ, കുഴപ്പമില്ല. താപത്തിട്ടായില്ലേ ഇട്ടായില്ലേ. ഇതിനകത്തോടെ സംസാരിക്കുകയും ചെയ്താൽ കുഴപ്പമൊന്നുമില്ലല്ലോ. ഇതിനകത്ത് കയറി കിടന്ന കാര്യം നമ്പർ കിടക്കാൻ വേണ്ടി പിന്നീട് കൊടുത്താലും മതിയല്ലോ. ഭാര്യ കയറിയില്ല, സാധനം കയറുകയാണ് നേരത്തെ. റിമൈൻഡർ കൊടുത്തതിന് തിരിച്ചെന്താ റിപ്ലൈ വന്നപ്പോഴേക്ക് തോന്നുന്നു വന്നല്ലേ. ഒന്ന് നോക്കിയാൽ അല്ലേ? ഞാൻ നോക്കിയില്ല. This session will begin within 10 minutes. നമുക്കിത് വലിയ തിരക്കാടി കേട്ടത് ഒതുക്കി നിർത്തിയാണ് ഇരുന്നോണ്ട് പറയാം ചെയ്ത് തുടങ്ങി. അവിടെ നിർത്തിയാൽ മതി. സംസാരിച്ചിട്ട്
Morning, bro, Sir Arnold.
Oh, was it
Good
muted?
morning. Yes,
Can you hear me now?
yes, we are for the session.
Did you? I'm sorry, I couldn't hear what you said. Can you hear me?
Okay, okay, I can hear you.
Yes, very. This is Ashish. Morning.
Good morning to all.
Can you hear me? Very?
Yes, yes, I could hear you very well.
Yeah. Yeah. Again, you can hear me. Professor Thomas. I'm asking Barry.
Yes, yes.
Good morning, process. Good morning. Good
Good
morning.
morning,
Yeah,
good
Barry is
morning.
not responding. Barry is not
Yeah.
responding. Doesn't look like he's hearing us. He can't hear us, looks like. Let's see. Seems like he's not able to hear us. Barry, can you hear us? Hello? Yes. Let's send him a message.
Just let me know when you want me to start.
ഇതിനകത്ത് മ്യൂട്ട് അവിടെ മ്യൂട്ടാണ് ഇപ്പോൾ അല്ല മ്യൂട്ട് അല്ല ഇതിനകത്ത് സൗണ്ട് പക്ഷെ അത് ഓഫ് ചെയ്യാൻ പറ്റും ഇത് പോകുന്നുണ്ട് അല്ലേ ഏഹ് അത് ഓഫ് ചെയ്ത് ശരിയാക്കി തുമ്മലല്ല അതിനകത്ത് വരും മ്യൂട്ട് അല്ലേ എനിക്കൊന്ന്
Nope.
അല്ല ഇതിനകത്ത് ക്യാമറ ഓൺ ചെയ്തിട്ട് അതിനകത്ത് സംസാരിക്കാം
Barry, can you hear us?
Yeah, I can hear you. Can you hear
No,
me?
We can hear you.
yeah, I can hear you. Yeah. Yeah, we can hear you now. We can hear you.
Okay. My voice is very low.
Now it is better. Now it is better. Now it is better.
Okay. Hi, Ashish.
Hi. Good morning. Good night. Whatever. Okay.
ഇത് ഓൺ ചെയ്യുമ്പോൾ കണ്ടോണേ ഈ സീറ്റ്
We have a minute, right, Satish? We have about a minute or so.
Okay.
മനസ്സിലാവില്ലേ കാണാതെ പറഞ്ഞാൽ ബാഗിക്കൊക്കെ മനസ്സിലാവും ചിലപ്പോഴേ ആദ്യത്തെ ഇതാരായിരുന്നു ഇൻട്രൊഡ്യൂസ് ചെയ്ത് നോക്കാം ഇതിനകത്ത് നോക്കിയിട്ട് എടുക്കാം വെച്ചിട്ട് ഇങ്ങനെ വെച്ചിട്ടെ ഇങ്ങനെ വിളിച്ചാൽ ഗുഡ് മോർണിംഗ് പറഞ്ഞു പിന്നെ ഇതിനകത്ത് തന്നെ തുറക്കേ കാണട്ടെ വിളിച്ചു എന്നിട്ട് 2-3 വീക്കല്ലേ ഉള്ളൂ സ്റ്റാർട്ട് ചെയ്തിട്ട് ചെയ്യട്ടെ. Good morning, Professor. Good morning. Yeah.
Yes, yes. Good morning. You can.
Good morning, sir. Good morning.
Yes, good morning.
Professor Barry Arnold, Professor. Professor Arnold. Professor.
Yes.
Yeah, good morning, Professor. I'm Professor Ilangovan from Annamalai. I visited you when I visited your department a few years back in the department.
Start ചെയ്തു.
Good morning, Professor.
Good morning.
അതിപ്പം 2 മിനിറ്റ് കൂടെ കഴിയുമ്പോഴത്തെ ഇനിഷ്യേറ്റ് ചെയ്യും, സ്റ്റാർട്ട് ചെയ്യും. അതിനെ വിളിച്ചിട്ട് ചെയറിനെ ഇൻട്രൊഡ്യൂസ് ചെയ്യാം. ഗുഡ് മോർണിംഗ് കല്യാണം സർ.
Professor, good morning, Satish Professor. Good morning, morning.
Good morning, Professor Langan.
Oh, sir.
Good morning, Professor Ashish.
Thank you. I'm here.
Yeah, okay, Professor. I'm very much glad to. I Rahul Gupta, Professor. I hope now we can start the session. Now 1 minute remind for live time, so that while that time we can utilize for introduce the chair. Naina is here in the group.
Yes, sir.
Okay. Just a minute. We can start now 8:15 a.m. and now few seconds only remains. You can introduce the chair and support the chair for the remaining part of the session.
Okay, sir. Hello, everyone. We are moving on to the technical session 24 of WSTA 2024, which is a keynote address that shall be chaired by Professor Yagin Thomas. Now, Professor Yagin Thomas is a former professor and head to the Department of Statistics, University of Kerala. He has granted the Emeritus Scientist by the Kerala State Council for Science, Technology and Environment from 2016 to 2019 and Professor Emeritus in 2013. He has more than 1,000 citations and 350 research publications to his credit, including on some modeling problems of statistics, estimation of the scale parameter of a family of distribution using a newly derived minimal sufficient statistic, as well as applications of ranked set sampling in estimating parameters of Morgenstern type bivariate logistic distribution. Dr. Yagin Thomas has always been a man of distinct vision and a constant source of support in all our events. So, it is with great pleasure that I cordially invite you, Professor, to chair the session. Without delaying you further, I once again extend a warm welcome to you and kindly request you to take over the session. Over to you, sir.
Welcome, sir. Please carry over the session. Hi, Professor Hira. Hi. Okay.
Good evening, good morning, Satish Kumar.
Good morning. Good morning. Good evening.
Very good morning, good evening to you, Barry.
Yeah.
Hi there.
Okay. Welcome, Professor. Welcome.
So we can start the session.
Yes, sir. Yes, sir. Please.
Okay, okay. Dear friends, Greetings of the Department of Statistics, University of Kerala to you all. We are now going to experience a very interesting session. Distinguished professor in the University of California, Revered Professor Barry C. Arnold. There is no necessity of an introduction of an international statistician of his stature to this audience. We all benefited, sir, very much because of your contributions and famous books on order statistics, record values, and so many topics. So, we are all eager to hear from you. You will be talking on univariate and bivariate Laplace and discrete Laplace distributions and generalizations. I hope we will be much benefited by your talk and request you to kindly come forward and deliver the talk. Professor Arnold.
Thank you.
കംപ്രസറൊക്കെ തന്നെ വലിയതായിട്ട് കാണുന്ന ആളാ മനസ്സിലായി. അങ്ങനെ അത് ഇന്നലെ മനസ്സിലാക്കണ്ടേ.
Come on.
Yeah, Professor, we can see you. See the slides. ഇത് രണ്ടായിട്ട് ഫുൾ സ്ക്രീൻ ആക്കാൻ പറ്റും. സ്ലൈഡ് ഷോ ആക്കണോ? അവിടെ ഇങ്ങനെ പോട്ടല്ലേ? സ്ലൈഡ് ഷോ.
Is that good?
Yeah, Professor.
Can you see?
Yeah.
You can see it?
Yeah.
Okay. I hope you can see the slides and also hope you can hear me. And I apologize if my
Very
accent.
very clearly.
Professor.
Yes.
So just make it slideshow more full screen, Professor. Full screen, possible.
You can't see my slides?
It is audible.
Barry, make it full screen. Make it full screen. Your slides are only covering half the page. Please make it full screen if possible.
Professor, whether you utilize the entire screen option? The same slide show in the ഏതാണ് മറ്റേ വിൻഡോ ആണ് ഉപയോഗിച്ചിരിക്കുന്നത്. ഞാൻ പറയാം അത് ചെയ്യുമോ ആവും നോക്കട്ടെ. ഫ്രം ദി ബിഗിനിങ് ക്ലിക്ക് ചെയ്യില്ലേ? Okay. Professor, while after sharing these slides, it's better to choose the entire screen instead of window, so that problem can be overcome. It is okay now, but it's better if possible.
Satish sir, won't it be better if we go to slideshow?
Yeah, that's what we are talking. And then instead of making it a confused way, there's a
Yeah. Slide from beginning.
Can you see it now?
yeah, from the beginning, while you are clicking, it is not working. That may be due to while you are starting from the sharing, you have not chosen the entire screen option. There is two options, entire screen and window. So instead of you choosing window, choose the entire screen. That may work well.
Okay. Share screen.
Okay, go to the So, yes,
Oh, it's mirroring.
Okay.
Oh, it's mirroring now. Now it's now it has stopped, sir.
share it once again, Professor, as you did earlier. Once again, Professor. Share the screen once again, Professor. Share the screen once again, Professor. Now it is share. Okay, it is okay. Please open that. You are in the right path. Just move to the slides only and press. Once again, Professor. Oh, share once again,
So
Professor.
he's on mute, sir. I think he's saying something. Professor is saying
You are
something.
muted. Your mic is muted, Professor. Your mic is muted. Yeah. Now please share the screen once again.
You have to click the present button on the meet screen.
Yeah, now it is fine. You can move to the slides. Yeah. Now it is fine, Professor. Now it is fine.
No?
Now it is fine. Excellent. You can move. Continue, Professor.
Can you guys see the slides now?
Yeah. It's fine.
No, it's fine. Okay, I'm going to assume it's fine now. Okay.
Okay, Professor.
Okay. I'm sorry for the delay. These things always seem to give me trouble. Okay. Hoping that you can hear me, I will continue.
Okay. Everything okay.
I'm hoping that you can see things. Thank you for. Are we okay? Okay, I'm assuming that you can hear me. So I'm going to report on some joint work with. What? You can't see this. It's not. They're not changing the slides.
നമ്മുടെ നെറ്റ്വർക്കിൻ്റെ ആണെന്ന് ഫോണ് ഫോണിൽ കുഴപ്പമില്ല. പ്രസന്റിങ് എന്നാണ് വേറെ ഏതെങ്കിലും ഉണ്ട്.
Well, I don't know what to do.
We can see Barry only, not the screen yet.
So please share it once again, Professor.
You can't see that, right?
Satish, maybe we can go ahead with this one.
Yeah, Professor. Yeah, Professor.
Let us go ahead with this one, please.
Yeah, it is okay. It is fine. Please.
It is okay. Let's go. It is okay, Barry. Let's go ahead with this. It's fine. It's fine. Satish, Yogin. Okay,
yeah,
right?
Professor, yeah. It is fine. It is fine, Professor. It is fine. You can continue.
Yeah. Barry, please
Can
continue.
you see?
Yes. Yeah, we can see.
And you can hear me.
I can hear you.
Okay.
We can. Go ahead.
Okay. I'm going to continue. And if it goes wrong, I'll just keep going. And you guys can just check your email if you can. Okay. Joint work with Matt Armenides. And we're talking about distributions related to the Laplace distribution, starting out with the symmetric Laplace and asymmetric Laplace, and then we'll look at some discrete versions of them, followed up with some bivariate versions, and end up even talking about multivariate versions. A little abstract, which will take more time to read and wish. We're going to look at various asymmetric univariate Laplace models. We're going to look at the general mixture model, which gives us even more flexibility. Spend time on parameter estimation, and then go into bivariate extensions. But much of the presentation will be related to discrete versions, because there's a lot more discussion in the literature of continuous Laplace densities than there is discrete. Okay. I'm going to begin by talking about the asymmetric Laplace model. And the simplest representation of an asymmetric Laplace distribution is by taking just two independent exponential variables with different, possibly different intensity parameters, lambda 1 and lambda 2, and just looking at the difference. Okay. Now, this is a classical Laplace density, and you can see it's an old friend. It's symmetric. The tails flow off at the same speed. It has a crest at zero. And so, it's one that you use in classroom exercises quite a bit. And it also arises in some situations where people think they're going to have error distributions that are not as heavy tail, perhaps, or not well approximated by a normal distribution. I guess. Okay, now so that's symmetrical. The asymmetrical skewed system is very, very simple. Remember, there's a difference V1 minus V2. And you can see it's speed may well be speed may well be and he uses a different parameterization, but this is the characteristic function. Like in fact, we can see how that works out by reminding you about a curiosity of the Laplace distribution, which probably you know. A symmetric Laplace variable can be represented in two ways, either as a sum of positive and a negative exponential random, or as a one-half mixture. That's kind of a strange property, but you can see how that works. Because in the first case, to get the characteristic function of V1 minus V2, we just have to multiply the two characteristic functions in this fashion. In the second case, we're going to take a half mixture. It'll be 1/2 of the characteristic function positive V2, and now V1, sorry, and 1/2 of the characteristic function V2. In this case, we're talking about symmetric case. It's very obvious that just by a partial fraction expansion, you get the second person. So they're exactly the same. Now, Chris Jones thought that was very unusual. He wondered if there were any other cases where you could plot a situation where you could represent something as a difference of exponential random, also a mixture, which not necessarily with this 1/2 function. And what Chris showed, it's helping in the exponential case so that you can do this, and most general situation is what we call asymmetric Laplace distribution. Okay. So with the asymmetric Laplace distribution, V1 minus V2, remember that, it's just the difference of two exponential variables. Suppose X has a distribution that's exponential lambda 1. That's a positive exponential random. But probably lambda 2 over lambda 1 plus lambda 2. That's a number for 0. And has that of a negative of an exponential, then probably 1 minus that, because lambda 1 over lambda 2. And curiously, that's exactly the same random variable that's expressible as V1 minus V2. And it is the asymmetric distribution, which we write down as 8L and 2. Remember, that was actually a different parameterization. It turns out that this parameterization has some utility. There's some things you can do with it that are more convenient than using mine, but I think this is the very simple parameterization and easy to visualize. Now, the mixture that we have, we could represent that using 3 random variables. A Bernoulli random variable with probability B equals 1, B is 1, B lambda 2 and lambda plus lambda 2, and 2 integer exponential random variables, okay, that are both exponential. And so we write X as B times B1 plus 1 minus B times minus B2. Well, after you shake out all the things there, that's just exactly the situation where you're going to observe B1 with probability lambda 2 lambda plus lambda 2, and you're going to observe B2 minus B2 from lambda 1 okay? And that immediately suggests, if it existed, the addition of introduction of a more general model with an additional parameter for flexibility. Why do we have to have P equal to lambda 2 over lambda 1 plus lambda 2? That seems to be contrived, and I'll show you in a moment why it is contrived. But so we'll have the same kind of model. Y is equal to, Y is just a Bernoulli random. Now with probably successive P, V1 is the exponential, and minus V2 is the negative exponential. And so this is a more general model. It includes the asymmetric Laplace as a special case. And you could test the hypothesis if you wish with a piece. That is the if we had chosen P density would here, with these things would shift in a continuous density, which we already know is the case with the asymmetric plus. So it's a more general model, and except for the again care taken near zero, it's a pretty nice density function to do. Okay, other bases is not continuous. A good reference would be asymmetrical cross distribution. I don't think we find the generalized asymmetrical cross distribution there. There's a paper that's incredible. By Krasnodowski and his colleague, Mr. Pakurski. They introduced the talk about asymmetrical cross distributions in some detail. Discrete versions of this distribution. And let me give you a little later. Discrete versions of this distribution. And let me give you a little later on that. In these situations, exponential random is shown, right? And in the generalized version, you can imagine, in the discrete version, geometric random with an exponential ones right here. Okay, before we do that, let's go into higher dimensions. So I'm going to think about trying to construct quite general bivariate asymmetric cross distributions. I'm going to do a little aside here. I talk about bivariate beta 2 models. Beta 2 distribution is the ratio of two independent gametes, as we know. And there have been several attempts to describe flexible bivariate beta distributions at the same time. Probably the most popular recent one is one by Ingram and one of his students, or a colleague, video. And there are lots of other things. The most general one round is one that was introduced by myself, explaining. And what we did, we set ourselves the task of saying, how could we construct the most general bivariate density? It's going to have beta 2 marginals, and it's going to be constructed by taking a whole truckload of independent gamma variables, each with their own weight. And we're going to put some of them in the numerator, some in the denominator, some in the numerator. So there are 4 places where an individual can appear. We have one of these where U1 only appears in the numerator. U5, for example, appears in 2 places, and U8 appears in 2 places. Now you can think about this thing. There are 4 different places where you could put a Van Gogh ISC. Just to put that one. 4 different Van Goghs can be allowed to appear twice. 5 appears twice. If another Van Gogh that appears twice, it will combine to 6. So you can't be more generous. And he said for this one, again, begin with 8 independent gamma. Just like before, individual parameters W. And define X1 now. Now this is a constant times the sum of independent U's. A constant times about the sum of independent U's, etc. And notice it's the same array of subscripts, 1, 5, 7, 3, 6, 8, that you saw when I asked you to try to remember. And so as a consequence, this represents the most general kind of model that can be constructed by taking a weighted sum of gammas minus a weighted sum of gammas, and in this case, weighted sum of gammas, weighted sum of gammas. But in such a fashion that we do have some dependent structure caused by the fact that, for example, U7 is in both. Now, not quite finished with this. Okay? We want to have an asymmetrical cross model. So that has to be a difference of 2 exponential random numbers. Well, if delta 1 plus delta 5 plus delta 7 were all summed up to 1, then the gamma distribution would that U1 plus U5 plus U7 would have a gamma distribution parameter 1, which is just a standard dimension. So what we will do is put 4 constraints on the deltas. Remember, 8 deltas. Whereas a weighted exponential and weighted exponential. That's the difference. Now, when you multiply an exponential, a standard exponential, by lambda 1 to the minus 1, it becomes exponential lambda 1. So this is exactly what you will want to have. It's a difference of 2 exponentials One would put a normal conditional distribution, a bivariate distribution which has normal conditions, x given y and y given x. The most general of this type is one's 8-parameter exponential thing. It includes your free, which is classical bivariate normal distribution, which uses 5. That new model gives you more flexibility than is available in classical bivariate. In some ways, it's simple, but it's going to be the same kind of structure. Begin with 8 independent, but now let's choose them to be exponential. Parameters landable to that. X to be the minimum of some of them minus the minimum of others, minimum of some of them minus the minimum of the others. And this is going to be this general model that you construct, which consists of, it's built of a bunch of independent exponential variables, and it's a form minimum of a bunch of them minus a minimum of another bunch of them. And the same thing. There's only one of the 4 slots, and it wouldn't be possible to have a being that could in 5 positions, because there aren't 5 positions available. We're going to have to show up and possibly even to have a being that occurs in 3 positions, because if it occurs in 3, maybe 5, 6, and 7, then the independent structure is needed. Okay, in this case, we write xy as a bivariate asymmetric line. Its parameter vector is just the vector of values, and this has 8 parameters as before. So it has the same type of flexibility in terms of dimensionality around the space as we had there. And now, before we go, there was a question. If it turns out, for example, that V7 and V8 are the smallest of 8 variables, then in fact x would equal 1 and double 1. So what happens is that this distribution has sort of singular nature, that there's positive probability that x is equal to 1. Unless you do some, you can avoid that by reducing the parameters. Now, submodels are obtained by just crossing out some things. So a submodel might involve V2, V6, and V4, V8. Otherwise, if you cross out V7, it has to be not V2. So you can have submodels which may well be adequate for your purposes in situations. Okay, generalized versions of these things are not going to. You can guess what to do, right? You just introduced 2 indicator Bernoulli random variables, P1 and E. Like one model, we just have I1 times lambda 1. Now you can see in this situation that this random variable here is indeed a generalized asymmetric variable, because U1, U5, U plus U7 has a exponential standard exponential distribution, which we've had the constraint that delta 1 lambda, that delta 1 plus delta 5 plus delta 7 is equal to 1. And then we have just multiplied by lambda 1 to make it into an exponential lambda 1, multiplied by this indicator variable. So it's exactly the generalized asymmetric. That's yeah. And a similar thing can occur for the distribution. Now, I promised you I wanted to spend more time in the discrete case because it's less ornament. Less, given less attention. In fact, Tomasz Prozabowski is one of the early workers on discrete versions. The roles played so far by exponential gamma variables are now going to be played by geometric and negative binomial. That's the trick. But the development in both univariate and bivariate cases is a very close parallel to the development of continuous cases. I apologize because there won't be many surprises. To the extent that I think that a lot of you can sort of think ahead of what's going to happen. And when I show up the slide, you'll say, oh yeah. So let's see how we can talk about an asymmetric discrete reference distribution. What we'll do is begin with 2 independent geometric variables, V1 and V2, probably different success probabilities. Now, I need to remind you what I mean by geometric random. For some people mean different things. A lot of people say that a geometric random should represent the number of failures preceding the first success. I'm one of those. And other people think it should represent the waiting time until the first success. The only difference is that one of them has possible values 0, 1 to it, and the other has possible values 1 to it. I think it's work nicely here. We choose our geometric random list to have possible values 0, 1 to it. So they are the number of failures preceding successful proof. Okay? Now, so it's just the difference in two geometries. Now, it's a discrete distribution, and we'll probably want to look at discrete density function, characteristic function, or the general function, and not probably a distribution function, which is just the thing that is a sum to it. And for x, if x is positive, for that to happen, it must be that for a given value of b2, b1 must be equal to x plus b2. Now, if we consider this any possible b2, plug in the loops of this because they're just two independent geometric parameters. And then, guess what? A geometric series of the sum. And of course, whenever you're talking about geometric random variables, you might notice that it's a geometric series over and over again, so you're not surprised with that. So this is our expression of the density. X is negative, and includes. And a very similar expression when x is negative, the only change is that q1 gets replaced by q2, and x now is replaced by minus x. Okay, so there's the density function, and then on the moment, you can see it. We now know that it's that. So the parallel there was the asymmetric plus. The only difference was that we had independent exponentials instead of independent and geometrics. Huh? Now, the a mixture that generalization street plus can be considered just as we did generalization of exponential to get an extra parameter for flexibility. It's the same setup as before. Remember B1 and B2 before were exponential, now replace them by geometry. And now there's one notational change that has to be made. This interface term, which is a primitive, you can't have it successful with P, because that gets the reader too confused. That P, P1, P2. So we'll use quiet. Okay, so this is the, and it turns out the density function of the generalized asymmetrical discrete density is really a little easier to write down than the non-generalized. Okay? And all of the three parameters range over 3.1, and the density is not hard because makes a bunch of distinction. If we had a set of generalized asymmetrical discrete cross okay. We might like to estimate the parameters, and the first thing you try in a model, if you have a new model, is you try to see if you can get an answer using it. Because first of all, that's probably an easier one to solve because I have a good feeling about what maximum likelihood estimates will do. Whereas if you use other techniques, harder to solve. So what we're going to do is we're going to define U to be the sum of the positive x's, V to be the sum of x's. Actually, it's going to be negative minus the sum of the negative x's, which makes it a positive random variable. We're going to define three other randoms. N0, the number of zeros, N1, the number of positive observations, and N2, the number of negative observations. So there are 5 statistics here, but really only 4, because if you know 2 of the 3, third. And minimal sufficient statistic could be N0, N1, U, V. You can take partial derivatives with respect to log right, with a log right input, and set them equal to 0, which is the standard approach for these things. We end up with 3 likelihood equations. So more comfortable, or you might say that we might say not so bad. They're particularly easy to solve if you have to have no zero observations in your sample, because that means that everything's on the right side of the system. And then you can just write down the solution for each of the by the various temperatures. This first equation gives you I hat, which gives you one hat. So otherwise, you're going to have to do an iterative solution, but it's not a hard theory. It does seem to solution. We can also try the same data configuration to use method of moment estimation. And then what we need to do is use probably. I think what I would do is set up U, B, and N0 and equate to their expectations. Solve the three equations that we get are down here. They're not pretty bad equations, but they do have to be solved. Okay. Now, at this stage, it might be natural to ask, can Tom Bayes help? And if there are any devout Bayesians and others, of course they will scream out, of course Tom Bayes can help. Up all the time. And so let's see what Tom can do for us. The right-hand function, we're trying to have it down here. It's a very nice expression, actually. And it turns into P1 minus P1, which kind of looks like terminal of the beta density. This looks like the P2 modulation terminal of the beta density. There's a thing here that is very more complicated, but it makes it quite natural to consider beta priors. And so we choose prior to pi, and if the pi square root is to indicate that it's endowed with prior density. It's beta, the parameters tau 1 and tau 2. And the pi tildes, which have been endowed with the beta distribution with parameters alpha I and beta I. And that's 6 parameters. And I'll come back to that, because how are you going to choose those? The corresponding joint posterior density is very simple, because a lot of these things combined with prior really nicely. And it looks very similar to the prior. It's not a conjugate prior. If n0 is equal to 0, quite happy to play around in this sentence. Okay. Now, we want to look at the bivariates. So we want to look at discrete versions of two asymmetric cross distributions. And again, we recognize that the is going to have geometric and negative binomial components, playing the rules that were played before for exponential again.
Okay.
Now, it turns out that the discrete version of the first generalized figure will always be symmetric, but the second kind will be possible without model. It will be possible to be asymmetric versions. Okay, here's the definition of the generalized version of the first kind of bivariate discrete cross distributions. And what we do is slightly different from the continuous case, because the generalized bivariate asymmetrical cross distribution, we had some lambda 1s, 2s that showed up in this representation. Geometric random multiplied by a constant. It's no longer geometric random. So those things have to go. But what we can do is, if you want to do two of the independent Bernoullis with modulus ij, and the good j is going to be independent negative binomial random. The other j and p, j equal 1, 2, and j. Now, what we want to have this to be the difference, or to be weighted by 1 times an exponential minus 1 minus I exponential. If you add up negative binomial randomness, you just get enough negative binomial random. But you can't get an exponential if you force the constraints of delta 1 Another those numbers, 1, 5, 7, 3, 6, 8, etc. show up again here. Set those two sides straight. The deltas to satisfy delta 1 plus delta 5 plus delta 7. The very same constraints we had. And if you do that, then the marginals, these things become exponential randomness, and it becomes just a mixture of an exponential and a independent exponential with an exponential with the same parameters. So this is just a spec Laplace, discrete Laplace. So in that sense, it does have margins of the discrete Laplace form, but it's not a discrete asymmetrical. You can write that as GB, or better here, generalized bivariate discrete Laplace the first kind with around phi to vector prime. But the deltas are subject to folding, and that's just the second. The second model is, I think, more attractive. Instead of just having a minimum minus the minimum, which is an asymmetrical Laplace model, we have I1, which is a Bernoulli random variable as before, I minus I2 is another independent component. And you can see with this construction, the key is the minimum of 3 geometric ranks, just like the minimum of 3 exponential ranks, is again a geometric rank. So in this situation, we do have I1 times a geometric rank minus 1 minus I1 times the geometric. So it indeed is a situation where we have asymmetric, discrete Laplace functions. And it's a 10 parameter model because there are 8 of the V's. Each of the individual geometrics has a 1 parameter
Hello?
delta algebra. And the
വന്നു
two
എത്തി
pi's
എത്തി വന്നു
2 parameter model. Okay.
ഇവിടെ ഉണ്ട്
Now, we can make things even more general because why do we have to have 2 independent ones? To see a more general construction, begin with a 4-dimensional random vector just takes on 4 possible values 1, 0, 0, 0, 1, 0, 0, etc. With probabilities pi1, pi2, pi3, pi4. And you want I1 to be the maximum of J1 and J3, and I2 to be the maximum of J2 and J3. In that case, I1 and I2, each one is a Bernoulli vector. They're dependent on it. You could use those I1 and I2 in the previous slide instead of these 2 variables. And that would give you even more flexibility and more opportunity to adjust the dependent structure of the bivariate density interface to the models described in this presentation. To be useful. So we got 8, 10, 7. Instead, there's sort of a port control model that is a source to give you a whole bunch of smaller, more manageable troubles. And you can check, you can test the hypothesis when you fill. Just like you're doing step up and step down regression to select among these subcolumns. Now, very few of the rules in the discrete case have discrete densities. And if they do have them, they're rather complex. And so, in the bivariate case, creative methods of estimation may be called for. Perhaps the most natural thing to try the variations of method of moments, and those things will work because they will give you consistent estimates. Usually, retain some kind of procedure. Okay, and so we said we can with submodels we have a device to allow us to cross out some if we talk about a negative binomial random variable with delta equal to 0, then we'll say u is equal to 0. And so they can be deleted from the some of the deltas 0. With the geometric models, if you set tau to 0, then B, corresponding B will be infinity with level 1 that's okay because you're going to take the minimum of some of the beads, but then that one won't have very low at all. So you could just as well have crossed out that bead. So in all of these forms to simple, you don't have to do any very deep thinking. Just cross out whatever beads and use that you don't want to. If you're crossing out BJ in one place and then here's somewhere else, you've got to take both. Okay, here's a very simple. Okay. This model is a library treating force model first one, and its parameter vector has been chosen to be just a one parameter family. The delta vector is just alpha 1, 1. And you can check to see that these things do satisfy the constraints on number 1. So delta 3 plus delta 6 plus delta 8 plus delta 1, etc. Okay, so it's a valid model. And we have a sample size n for that distribution. This is the function. And you can verify the zero occurrences are very nice. And just setting up two natural statistics as the moment estimates. And in fact, and the other ones have been constrained so there's a dependent structure on them. The model is very simple. It's a library beta 2 distribution. Set up the two same kind of statistics, and you end up with two moment equations which can be solved, but I think they have to be solved iteratively. So you just choose an initial value graph and then solve for beta and see the inverse equation, etc. Okay, so that's standard. Now, don't have much more to say. Higher dimensional versions can be considered. The trivariate version of the asymmetric discrete Laplace model type 2 involves 26 independent geometric components, each with its own calculator. So only a submodel fraction of each. And I don't think I'll talk about this one. This is a submodel of a trivariate. But this is a trivariate. It only involves 1, 2, 3, 4, 5 of the 26 variables. But it's a valid which does indicate, does exhibit the kinds of margins that does exhibit dependence. Okay, so the model is a performant. So there are 26 geometric variables around there, and that's just a surprisingly complex extension of the model that we saw way back, which were the vibrant giant ball things. That's related to this. And now, just to help you out, what did we come up with 6 triangles, 2 dimensions, and 8 dimensions. 3 dimensions is 26. If you're alert, that's just 3 to the power 3 minus 1, 3 squared minus 1, 3 cubed minus 1. So the next one will have 80 dimensional model, etc. And it's a lot of situations where we mentioned 8 parameters, the fully flexible hybrid is not that uncommon. And so, though almost nobody ever talks about them, 26 parameters for a fully flexible hybrid distribution seems to be needed to have. Okay. Now, once again, my reservation, I don't expect you to rush out and use all of these simplified submodels by setting many of the delta j's to 0, the right thing to do. So, for example, it's a valid model. And then references, the one that I want to mention mostly is the work of Kozlowski and Podgorski, who are misspelled twice. I should get negative points for proofwriting, reading, and positive points for consistency. And that was Chris Jones, my co-author, National Benitez, an old paper with Tony Hay, and then a paper somewhat related to some of the. Thank you very much for your attention. sure it went very fast. And I will be happy if you have any interest. I'll be happy to send you copies of the transparencies and correspond with you any action. My email address, Barry.Arnold, first name, last name, at ucr.edu. I'm still vaguely associated with the University of California, teachers, and an emeritus professor. And finally, I'll sign off by taking you to my hometown. And if you come into Huntington Beach, as you come into town, you'll see a sign that says, "Welcome to the Surf City." And I know whenever I show this picture, people say, "Where are the surfers?" I find them funny. They're hiding here in the piers, and they're hiding because this beach was supposed to be closed for COVID. So those guys, being enthusiastic surfers, they're not going to listen to the government. So anyway, last comment, I thought about getting T-shirts printed with this on it, with the idea that when I go through customs immigration in various countries, the customs officer will undoubtedly feel obliged to call with Superior to discuss the secret code on this gentleman's T-shirt. Okay, thank you again for your attention.
Okay, Professor, thank you very much. Okay, Professor, thank you very much for the talk. We have to move to next session.
ക്യാമറ
Uh,
ഇല്ല ഒന്നില്ലെന്ന് ചോദിച്ചത്.
your talk is very, very interesting. It involves univariate Laplace distribution, asymmetric Laplace distribution, bivariate versions, discrete Laplace distributions, and its bivariate extension. Very interesting, but there was trouble in the display of the screen, but still we have enjoyed a lot. So we are actually running short of time. So question hour, we will have any one quick questions.
Satish has a very quick question.
Yes.
Barry, just a very quick question.
Yes.
This is Ashish here. Yeah. I was wondering for the BAL1 and BAL2, how do the characteristic functions look like?
If there's a generalized ones, they're just mixtures of a very simple ones.
Not readily right away available. We need to work on that.
Yeah,
Okay.
I don't think they're easy to write down because of the fact that
Okay.
the VR here one.
Thank you. Over to Satish. We enjoyed your talk, Barry, very much. Thank you.
Thank you. I do hope you can hear.
So there is no time. So on behalf of the organizers of this conference, I extend a cordial thanks to you, Professor Arnold, and very thank you because we have accepted our invitation and joined with this Google Meeter. Once again, thanking you. I conclude.
Thank you. I enjoyed the opportunity.
Thank you, Professor Barry, for your wonderful talk. We enjoyed the talk very much. Thank you. And also, thank you, Professor. Thank you so much. Thank you so much. Also, we would like to extend our gratitude to Professor Yagin Thomas for chairing the session. And now we have a sort of time. We just move to the next session. Thanking you, Professor. Thank you, Professor, once again. Thank you, all the professors, Professor Ashish, Professor Hira, and all other professors also there in the group. Thank you, professors, for your presence, and that makes the conference, this session more powerful, and we are honored through your presence, professors. And now let us move to the next session. In the next session, we have three speakers. The first speaker, Rudra Pradhan, is here in the group. I hope so. Is from IIT Kharagpur. Dr. Krishnakumar from University of Kerala is here in the group to chair this session.
Raji will introduce the chair.
Raji.
Thank you. Can you hear me?
Yeah, we can hear you.
Yeah, thank you. I thank Professor Satish and Dr. Riaz for this opportunity. We have with us our first session. We have with us Dr. Rudra Pradhan, who is a SAP fellow and is also an associate professor from the Indian Institute of Technology. Who there he has been associated with Vinod Gupta School of Management and
Yeah, is it visible now?
yeah, it's visible. You can make it full screen.
Yeah, I'll do